been doing is look at a flood. Last class, what did we look at last class?
The mean motion.
Right, mean motion. Look at
An eccentric anomaly.
mean motion. And we also looked at mean anomaly. Okay, and we revisited Fu anomaly. Okay. Now, to understand in the context of orbital mechanics, what does anomaly mean? Huh? It's an angle. Okay. So this anomaly is nothing but always an angle. What was the intent of looking at eccentric anomaly? We discussed that last class.
Does it have to do with the whole knowing where the body is for a certain period of time, or was that the mean medium?
Eccentric anomaly. Critical for expressing
The angle in time.
as a
Function of time.
function of time. And how do we do that? We have Kepler's equation, which is n into. So you should understand this form of Kepler's equation as well. E minus T is equal to E minus E sine E. Okay. And what is Gauss's equation?
Tangent E over 2.
Tangent of
E over 2.
E over 2.
Equals the square root of 1 E plus 1 plus E.
1 minus E divided by 1
Tangent of theta over 2. The first equation you said is another form of Kepler's?
Right, so if you remember what we did here was we just used T, right? The other thing. So what does this mean? What does that T? So this is not the orbital period. Okay? Don't confuse it with orbital period. Capital T. So these two are very important equations. Time of last axis You understand guys the meaning of time of last periapsis passage?
Understand the meaning of what?
The meaning, time of last periapsis passage.
No.
So what that means is, if you want to figure out what is the duration of your exam, so what you do is, not the duration, if you want to figure out when your exam finished, right, you figure out, you first, this is the time when the exam starts, okay, and this T is what? The duration of the exam. So from that, what are you going to know? You are going to know that this is the time when the exam finishes. So you will know the duration of the exam. Okay, this is the other form. So from that, so this T will always be what? Time at, if you look at this. This is your periapsis direction, right? This is T is time at this position. Okay? You have your focus here. You can take this could be P. This position, let's say T1. Okay, T1 is position at T1. So this would be what? Again, let's say there's another orbiting body. The orbiting body is here. Okay, so we have T2 at position P2. You see it? Okay. This time T is, you note down the time when it crosses the finish line or the start line. This is like a start point. Okay. Since it's the periapsis, that's where it starts. So you can figure out, if you know what is the time at this position, if you know what the time at this position, then you can figure out this E. Got it? So if you know that N is what? N is simply the mean motion. Okay? How do you calculate N?
The F of R plus G of V.
2 power over T, the big T.
How do you
2
calculate
pi.
what?
N is 2 pi over T. N is mean motion. Mean motion is what? Simply angular velocity. Right? How do you calculate angular velocity? Can you think of a
For angular velocity, you do R cross the V. To get angle. I thought it was angular velocity. Oh.
that's angular momentum. Angular velocity. You understand velocity, right? What is velocity?
Like the speed. Like, you know, your velocity.
What is it? Velocity. Change in position over time. What is angular velocity? Huh? Change in angular position over time. Right? So you have, so what is the angle here? This angle is theta 1 This angle is theta 2. Okay. So if you want to figure out the angular velocity from this point to this point, what are you going to do? From point P1 to P2? Hmm? Hmm?
Say one time.
If you want to calculate the mean angular velocity between points P1, point P1 is this, P2 is this. What are you going to do?
So wouldn't it be the difference in the angles over that T?
Yeah, it will be theta 1 minus theta 2 divided by T2 minus T1. T2 is what? Time at this instance, right? T1 is time at this instance. So this will give you the angular velocity. Got it? Mean motion is nothing but this entire thing. So you calculate the time at this position, and you calculate, sorry, not calculate, but you measure the time. You keep a track of the time at this position, and when it completes one orbit, you again keep a track of the time. You just figure out what the time is. So how much angle would it have covered if it came back to this point?
2 pi.
Huh?
2 pi.
2 pi or 360 degrees. 2 pi over, this is the period of the orbit. That T, capital T is the period of the orbit. So that is the mean motion of the ellipse, the mean angular velocity. Got it? What is mean about it? Huh? So what is average about it? Why do you say mean? No. So what is happening is, here the orbiting body is at its fastest, at the periaxis. Here it is at the slowest. So the mean time, if it were traveling at mean velocity, it would take so much time to cover the entire distance. Okay? So that is the reason they introduced mean. Because for ellipse, it travels at different velocities. For circle, it will always travel at mean velocity. Always traveling at a mean angle. Okay. So what we did was, the other thing we were discussing last class was this.
Dr. Sunny, what's the variable, the sign that we use for angular velocity?
Huh?
What is the sign that we use for angular velocity?
Angular velocity, we use here. We use simply this omega or this omega. You have to remember this equation. E dot is equal to A square dot plus omega cross with A. You remember this? So here this omega is the angular velocity of the frame. This is you have to be slightly careful with angular velocity and rate. What is the difference between angular velocity and rate? You know what rate is? Rate, so we will use velocity is synonymous, if it's synonymous to angular velocity, okay? Speed is synonymous to rate, angular rate. Got it? So this is regardless of the direction. This is a vector. These two are vectors. These two are scalars. Now let's go back to this. Okay, we need to understand a little bit of orbit propagation. You understand what propagation is? What does your GPS do? Huh? GPS does not show the map. GPS will give you what?
Direction. Your position.
Position. So GPS is used for absolute position determination. When you map that onto your map, when you take that position, it will give you coordinates, right? GPS satellite itself is only designed to give you precise coordinates, precise latitude and longitude. So when you put that latitude, longitude onto a map, when you relay that onto a map, it tells you how that position is changing. That's how it will give you how you're navigating, right? That is position determination. You understand determination? That is absolute. Every time you use a GPS, it determines the position, it determines the absolute position. The GPS satellites are, we always know where the GPS satellites are in a particular coordinate frame. Okay? So when we are sitting in a car or we are using GPS, we use the triangulation principle to figure out where we are with respect to the GPS satellites. It's called absolute position determination. You understand position determination? How do you propagate that? If you lose GPS, your GPS unit still works. What is happening?
So it's going to look for you at another point.
Huh?
So when the GPS isn't going to look for you, to reach another point on the projected route. So when that usage.
See, if your GPS signal is lost, if you're in the woods, let's say, your instrument doesn't automatically stop working. Still keeps working. It still keeps giving you the position, incremental position. How does it do that? It uses something called accelerometers. You know what an accelerometer is? You've heard about accelerometer? No?
And the one that gives you a speed?
Accelerometers, by definition, what should it give you? Acceleration. Okay. Accelerometers are very nice devices. They work on the principle of Newton's second law. Okay. F is equal to ma. They are designed to give you acceleration. Okay. In whichever, so generally you have a triaxial accelerometer. What is a triaxial accelerometer? 3 axes. Why do you need 3 axes? You always are accelerometers gives you acceleration. Acceleration. This is positional acceleration or translational acceleration. You understand translational acceleration? Can you accelerate any other way? You can accelerate. You can have angular acceleration, right? Can you have angular acceleration? You can have angular acceleration. Gravitation is what? Angular acceleration, translational acceleration. Alright, let's not. Acceleration can be translational. Always think about 3 degrees of freedom. So 6 degrees of freedom. Translational, rotational. So this is also related to translational rotation. Acceleration is also related to translational and rotational. So when you do accelerometers give you increments in what direction you are accelerating. At that instance, what is your acceleration? That is what accelerometers give you. So if you have acceleration, how how do you extract position information out of that? Come on. How do you extract position information from acceleration? Clayton?
Second.
Huh?
Second.
No, it's not
Yeah. You integrate it twice, right? What are you going to get if you integrate it twice? Position. So you're going to get the relative position. See, if you accelerate, if you integrate acceleration, this thing, between two time frames, if you do a definite integral, what are you going to get? The position between this point and that point. Okay? So when you can use this accelerometers to supplement your GPS systems. Okay? You see it? So that is how your instrument keeps working. And this is something you as space engineers should absolutely know. As space engineers, as somebody using technology, your cell phones are always equipped with accelerometers. That's the reason. How does your cell phone recognize when you turn it? What is the mechanism? Accelerometer, but how does it work? You're right. What does it figure out? Huh? You have a triaxial accelerometer, okay? What is, huh? When you rotate it, your screen changes, right? Your screen rotates. When you physically rotate this thing, your screen adjusts. How does that happen? Huh? Gravity. So what your acceleration does is, there is always acceleration due to gravity, right? So if you have a sensor like this, there will be 3 sensors always. 1, 2 and 3. Again, these 3. When you rotate, so at this point, which sensor is experiencing acceleration due to gravity? This one. Okay. So the reading of this sensor is the highest. Okay. When you physically rotate your phone, which sensor is experiencing acceleration due to gravity? This one. So it immediately senses that this is the direction of the cell phone. Now let me change the screen this way. That's how it works. Okay? And there are similar something called gyros. You know what gyros are? Gyroscopes. So there are gyro sensors which work to give you angular rates. Okay? Those give you angular rates. So when you are rotating, when you are playing your games, right? Those are gyros. So gyros combined with accelerometers will give you how you're changing what is your motion, your angular and translation motion. When you do orbit propagation, did we do orbit determination? Orbit determination. We did orbit determination actually. So given R and V, you were required to figure out the orbital elements, right? So that was orbit determination. Okay. So what is orbit propagation? Orbit propagation is given or known R and V at time t naught, find R and V time t1. Okay. So this is what we were discussing last class. Okay. So this is your again your p direction. And you know the position. Let's say this is the position, right? R naught. This is the velocity at this direction, E naught. We talked about how do you figure out the position at some RT and the velocity dt. Okay. So this is orbit propagation. So what you know is, can you use GPS to do orbit to calculate this R and V in an orbit? Yes?
Can you use what?
GPS? You sure? Huh? To calculate any orbit?
So like, even like when we're going in a circular path, we always have to position and rate. The last two so.
Thank you.
So can we calculate the position and velocity using GPS? Can you calculate the position, orbit position, and or determine the position and velocity when we are in on orbit?
Yeah, probably position, but I don't know about velocity. Will the GPS give you velocity? Is that what you're asking?
How do you calculate the velocity from position? Huh? Just take a derivative, right? You can get the velocity. You know the derivative, right? So how do you calculate the? Does GPS give you position and velocity if you are in orbit? As long as where are the GPS satellites? All GPS satellites are geosynchronous, right? As long as you're below the geosynchronous satellites, the geosynchronous orbits, it will always give you the position. Okay, it will always give you the relative position. What happens if you go outside? It may not give you, because it's always pointed towards Earth. GPS satellites are pointed towards Earth. So you may not receive, the signal may not get to you if you go outside. See, that is the reason GPS, we are so dependent on GPS today, we don't realize how difficult it is to figure out position. Position is always relative. Okay? So when you go on Mars, what do you do for position? For determining the position of the, let's say, the rover. Position of the rover. How does the rover itself know where it is? Huh? Based on, exactly, so complete that. You've still not completed that. So that is the challenge. These GPS satellites, we are so reliant. Once we go outside, we do something called simultaneous localization and mapping. So the rover, what it does is, when it lands, it kind of, calculates or references that point, and from that reference point, every other position is calculated, or it does the incremental study. So every time it will do some image processing to do its position calculation, and it will say I am this much far from my initial position. It has to say that. Otherwise, it cannot say Mars itself is not that well mapped, although they are trying to map it. But it is not that well mapped. It doesn't have latitude, longitude so well mapped, right? Unlike Earth. So what this does, as long as you're below the GPS belt, we will always be able to figure out the absolute position and velocity. Okay. But so what I told you yesterday was not yesterday, but Tuesday. This R at time t can be expressed as f r naught, and this is, let's say, say time t naught plus g into velocity at time t naught. Similarly, v is f dot okay. Did you follow this discussion from Tuesday? Right? So any triangle, if you make a triangle out of these three, what three are we talking about? We are talking about R, R naught, and V naught. Okay? There will always be some relationship which can be established between R, R naught, and V naught. Right? So that is what we are trying to do here. This F and G are simply multipliers. It's just a very linear relationship. If you know how, see, this is very well defined motion. Right? How is this motion defined? What defines this motion? What expression defines this motion? Huh? Huh? What expression defines this motion? John Lewis?
What expression?
Clayton? See, this is what you're here to think about, huh?
Another second one? Are you talking about the motion?
Yeah, what defines the motion? How do you define the motion? What expression defines the motion?
The angular velocity.
The two-body problem statement defines the motion. That is what I keep telling you. Think. You guys don't think. So you have to practice, Raju. This is the reason we are learning this course. Okay? So if I ask you again, what defines this motion? The two-body problem statement defines the motion. Or the Kepler's first law would have been an acceptable answer. Kepler's first law is orbit equation. That will define the motion.
Relational motion. Relational equation.
The orbit equation.
The two-body relational.
The two-body relative motion is the problem statement that defines the motion. So that there you have acceleration and position. Okay? And the solution to that is also defined. So this motion is very well defined by this equation. Okay? R double dot plus mu over R cube R equal to 0. Okay? So that means we know how this F and G will change as a function of this R naught and V naught. If we know R and V, we can express this F and G as a function of R and V. Okay. Also, if we know that if we take the derivative of this V of t is nothing but the derivative of this, right? Why didn't I use the product rule here? You should have questioned that to me. Although I mentioned it last class. How do you take the derivative of this? This into derivative of this plus this into derivative of this, right? You don't see that why? This R naught of t is like a constant because it is predefined. That is the position at that point. That is not changing. R naught, RT or R of T naught or R naught is not changing with respect to time. It's an established position at time T naught. So if you take the derivative, only this, we just need to take the derivative of F dot and G dot. Okay? And the expression, you need this for F and G can be expressed as F and G Taylor series. You remember Taylor series? No, not really. F and G can be expressed Also, this relationship is very important. F G naught minus F dot G is always equal to 1. This is something you can expect for your exam. Prove that. Prove that. Is there an easy way to prove that? If you are given an orbit, what is constant for an orbit? What are the constants of motion? If you do, you have R given R P, R is equal to, so I'll just use this R is some F R naught dot plus G, and then you have V is equal to F naught R cross V. What is R cross V? H. And what is H? What is what is special about H?
Specific angle.
And what is special about H? What do you know about H? Huh? Huh? H is not 0, Alex. H dot is 0.
It's conserved.
It's conserved. What does that mean? It's constant. That's what I asked you. The initial question was, what are the constants of motion? So H is one of the constants of motion. Angular momentum is conserved, linear velocity is conserved, total mechanical energy is conserved. These three you have to know. Okay? So this R cross V is nothing but F R naught plus G V naught crossed with F dot R naught plus G dot V naught. Okay? So this is what F dot R naught crossed with R naught plus F V dot R naught crossed with V naught G F dot V naught crossed with R naught plus G dot V naught crossed with V naught. So this is 0. This is 0. So what you have here is, why is this 0?
The vector cross with the same vector.
The vector cross with itself is always 0. So what you have is F G dot minus G F dot R naught crossed with V naught is equal to R crossed with V. What is this value? H. What is this value?
H.
It is still H. That is conserved means. R cross will always be same. So this need not be H naught. H naught, H of t, it doesn't matter which point you are in an orbital. This R cross V will always be the same. R1 cross V1, R2 cross V2 will always be the same. Will always be H. So you can just say this is 1. Okay. So what you're going to get is F G dot minus G F dot is equal to 1. Where did this minus come from? You did not notice that?
Did you write that 1 up there? That 1? Did you write the number 1?
Right. So you cross H and H cancels. You get 1.
So with the R cross V and the V cross R.
Where did the negative come from?
That the cross vector of R naught and V naught, they are changing their
Right.
position.
They're changing their flipping, right?
Flipping,
So R cross V is, or A cross B is always negative of B cross A. Okay, so that's how you get that. I'll give you an expression for FG. Branch coefficient. Let me get it.